So let's take the 2 wattmeter method. Okay, so we have to take one load. So we have to take one load. For that load, we have to connect 2 wattmeters. So I will tell you where to connect those 2 wattmeters and check the power across those 2 wattmeters, whether it is giving the complete 3-phase power or not. That's we have to understand. Okay, so again I will tell you this one. So we have to take one load here. Okay, so we have to take one load. For that load, we have to connect 2 wattmeters. I will tell you the connections, how to connect, and after that check those wattmeters whether that is giving complete 3-phase power or not. If they are giving the complete 3-phase power, then 2 wattmeter method works. Understood, right? So we have to check that. Understood, right? So anyway, 2 wattmeter method works for balanced connection or unbalanced connection, whether it is star connection or delta connection. What we have to study, for which load we have to study means, in general you have to study for all the loads. Okay, it will work for all the loads in general. Okay, so we have to study for every load, but our exam point of view, our syllabus point of view, we have to study for balanced star. Understood, right? Again I am telling you, for our syllabus, okay, balanced star is very, very important, and it is there in our syllabus, not the other one. Okay, so balanced star connected load we have to take here. Understood, right? So I am just taking a balanced star connected load. Okay, you can understand, a balanced star connected load we are taking. Okay, so a balanced star connected load we are taking. Okay, so anyway, star connected load, right, we can take, and it is balanced. We can take 3-phase 4-wire or 3-phase 3-wire, anything. Okay, so star connection means possibility of 4-wire also, right, neutral wire. Anyway, it is balanced, right, no current will go through the neutral. Okay, so we can take as 3-phase 4-wire or 3-phase 3-wire also. Okay, so I am just taking a 3-phase 3-wire connection. Okay, so first load, okay, first load we have taken, and second load also we have taken, and third load we have to take. Okay, so like this, all the 3 loads connected in star connection like this. Okay, so all the 3 loads we have just taken and connected in star. Okay, star connection it is. Understood, right? So anyway, this is star connection, right? I am just taking the phase voltages. I am just taking the phase voltages. The voltage across this one is VA voltage. Okay, so otherwise you will take as RYB. Okay, that will be more useful for you to understand. So VR, okay, R phase, this is R phase, and this is Y phase. I'm taking this one as Y phase, and this is B phase. Okay, 3 phase we are taking. And if you ask me what is the phase sequence of this, what is the phase sequence of this means, RYB phase sequence I will tell. Okay, so we might have know about this one. So what is the phase sequence means, we should not count in anti-clockwise direction like this. Okay, these are the vectors these are, otherwise the 3-phase loads we have to consider. So first R phase, after that which phase is coming after 120 degree, Y phase is coming, they are all rotating. Okay, we have to give your hand here and check. Okay, first R phase is going, these are all rotating in anti-clockwise direction, right? So after that Y phase is coming, after that B phase is coming. Understood, right? So anyway, these 3 are rotating in anti-clockwise direction like this. After one phase, another phase is coming. What is the phase sequence here? So phase sequence is R, Y, B. Okay, so R, after that Y will come, after that B will come. Some lecturers will tell like, so vectors are rotating in anti-clockwise direction only, but while counting you have to count in clockwise direction. Wrong. Okay, so you may get the correct answer, but analysis is wrong. Okay, so vectors are rotating. Why we have to move your hand to understand? You have to see the vectors. Okay, see from the top or any place. See from here. First what is going? B terminal is going. After that R terminal will go. After that Y terminal will go. B R Y. Otherwise we can write down as, okay, so R Y B also. So, okay, take this one to the other side. R Y B. Otherwise you can take as Y B R. Okay, everything is same. After that B R Y. Okay, so everything is same only. Any sequence if they have mentioned like this means that is nothing but RYB phase sequence only. only. Okay, so see, B phase is going, after that R phase is coming, after that Y phase is coming. So that is how we have to take the phase sequence of any vectors. Understood, right? Any vector, whether it is voltage, current or anything, we have to take like this only. Never move your hand like this. Why we have to move your hand? To understand that they are already rotating, right? You just have to see. They are already rotating, the vectors already rotating in anti-clockwise direction. See how they are rotating. After one, which is coming? Okay, R phase is going, right? Y phase is coming. After that, B phase is coming. We have to understand like that. Okay, understood, right? So this is RYB phase sequence. We have understood this one. Okay, so anyway, so phase voltages I am giving VR voltage, and this is VY voltage, okay, and this is VB voltage. Understood, right? So anyway, ZA, ZB, ZC all are same only here. Yes or no? All the impedances are same. Why it is same? Because it is a balanced load. Understood, right? We have taken a balanced star connected load here. That means all the impedances are same and their angles also same. Okay, at an angle of phi, Z and at an angle of phi, Z at an angle of phi. That means there is some current in this one. There is some current in this one. What is that current? I will take this one as IB. I will take this current as IY, and this current as IR. Okay, so I have just taken the currents IR, IY, IB. Now what is the angle difference between this VR and IR? That will be equal to this phi. Yes or no? The angle difference between VR and IR is phi only. This phi is nothing but the impedance angle of this one. So if you take the current in this one and current voltage in this one, so what is the angle difference between those two? The impedance angle is nothing but the power factor angle for this load, because only one load is there. Understood, right? If any other load is there, both power factor, both impedance angles you have to make as the single one. Okay, equivalent you have to calculate. After that, we have to calculate the equivalent angle. Understood, right? So like that we have to see this one. Okay, so the angle difference between VR and IR is phi. Similarly, angle difference between VY and IY is also phi. Angle difference between VB and IB is also phi here. Okay, we have just given the three phase load. Okay, not connected any wattmeters here yet. Understood, right? We have not connected any wattmeters yet here. Okay, so we have to connect some wattmeters. Understood, right? So anyway, how many wattmeters you have to connect? We have to connect only 2 wattmeters here. Understood, right? Only 2 wattmeters you have to connect. So I will tell you where to connect these things. So I will just connect 1 wattmeter in R phase. That means current coil in series with load, current coil in series with load, and potential coil we are connecting. Okay, so this is the potential coil we are connecting across the load. Okay, so I'm just connecting here. Okay, across some load. Okay, so across this some voltage has to be up here. Okay, so across the load some voltage has to be up here. This is RSC. Okay, this is potential coil, this is current coil, and this complete one is nothing but 1 wattmeter. Okay, so W1 we will take. Okay, so W1. Understood, right? So first wattmeter it will be. Understood, right? So anyway, second wattmeter you have to connect. Where to connect means I am connecting in Y phase. Okay, so after this is R phase, this is R phase, and I am connecting in Y phase. Okay, so I will connect the current coil in series with load. Okay, current coil I have connected in series with load, and potential coil we have to connect across the load. Okay, so potential coil I have taken, and for the production of this coil, so I am connecting the resistance. Okay, RSC we have already discussed it, right? We have to connect one series resistance for the protection of the instrument and the protection of the load also. Okay, across the load, across the potential coil there should be some voltage that should apply. Understood, right? So anyway, we have connected 2 wattmeters. This is nothing but second wattmeter. Understood, right? So this is nothing but the second wattmeter. Okay, so we have connected 2 wattmeters. This is potential coil, this is current coil, and this is wattmeter number 2. Okay, so this is the B phase. Okay, B phase line it is. Okay, this is B, this is Y, and this is R. Okay, so we have just connected 2 wattmeters. So this is W1 and this is W2. Okay, 2 wattmeters we have connected. We will check these wattmeter connections and what is the wattmeter reading in first one and second one. Later we will go whether it is reading the three-phase power or not. Okay, so this is a star connected balanced load. Okay, star connected balanced load we have taken. So you may get doubt, can we take delta connected load? You can connect, no problem. Understood, right? You will get the same type of analysis. Okay, and can we connect unbalanced load? You can connect unbalanced load also. For everything this method works. Understood, right? But your exam point of view, whatever formulas you will get here for the balanced star connected load, whatever formulas you will get, so those things will be work for you. Understood, right? So that's why I'm giving this method. Okay, you can try for other methods also, same however we are doing the procedure, everything you have to follow like this only. Understood, right? Okay, we will write the wattmeter readings. Okay, W1 and W2 now. Okay, so let's take W1. What is the W1 reading? The wattmeter 1 reading is, so we have already understood, wattmeter reads the voltage across potential coil into current in current coil into the cause of angle difference between the voltage and current, whatever it is. Understood, right? So let's take, what is the voltage across this potential coil? First wattmeter W1 we are writing. So voltage across this potential coil, that means voltage between these two terminals. Tell me what is the voltage? So it will be the voltage between these two. Understood, right? That is VRB. Yes or no? The voltage difference between these two is VRB. Okay, so R2Y, R2B we have to take. Okay, so that is VRB into the current in current coil. What is the current in current coil? So current in current coil is IR only. Understood, right? So IR is nothing but line current here, but here it is phase current. This is star connection, right? Line current and phase current will be same. Okay, so we will just take this one as IR. Okay, so IR and cause of angle difference between, so tell me cause of angle difference between VRB and IR. Okay, so actually what is this 5 we have taken means the angle difference between voltage and current we have taken. What is that voltage? This VRB voltage. What is that current? That is IR current. Okay, so angle difference between VRB comma IR. Understood, right? So anyway, the angle difference between VR and IR we have, that is as phi. Yes or no? The angle difference between VR and IR, okay, phase voltage and phase current is phi, but this is line voltage and a line current. This is also a phase current also, but we don't have angle difference between VRB and IR. Okay, so we don't have this angle directly. We have to check that angle. Okay, later. Okay, by drawing the vector diagram, we have to understand that angle. Understood, right? So anyway, W2 we will write. Okay, wattmeter 2 reading, that will be equal to V. What is the voltage across this one? Wattmeter 2. Just see across the potential coil, what is the voltage? So that means between this point and this point. Okay, so what is the voltage means? So you can check, this is the voltage, that means VYB. Okay, so VYB will be the voltage across this potential coil. Okay, second wattmeter potential coil. And what is the current in this current coil? That will be IY. Okay, yes or no? Current will be IY here. Okay, so anyway, YB into IY into cos of angle difference between VYB comma IY. Okay, so we have to find these angles. Whenever you find these angles, then only you can calculate the complete power whatever these are measuring. Okay, W1 and W2. Okay, these wattmeters are giving some readings. We have to understand whether this complete reading is total three-phase power or not. Okay, so we have just taken one load, checking whether it is working or not. 2 wattmeter method is working or not. Okay, understood, right? So to understand these angles, we will just draw the vector diagram of this. Understand, right? Vector diagram of these voltages. Okay, voltages and currents. Okay, so I am just taking R phase, Y phase and B phase voltages. Okay, so R phase. Okay, we will take R phase VR and Y phase, which is 120 degree apart. Okay, so this is Y phase and this is voltage VB. Okay, so three voltages we have given, VR, VY and VB. Okay, so and what we need VRB and IR. Okay, and similarly VYB and IY. Understood, right? So anyway, I will just give the currents. Okay, currents. Now tell me, this is lagging power factor we will consider. Okay, generally this will be, in general, which type of loads will be there means many of them are inductive loads. So I am just taking this one as a lagging load. Lagging load means inductive load only. RL load it will be. Understood, right? RL load we have taken. That means current lags the voltage or voltage lags the current in RL load. In RL load, current lags the voltage, we know already. Understood, right? Otherwise, voltage leads the current by an angle. What is that angle? Between 90 to 0. We know that, okay? For the perfect resistor, it is 0 degree. For perfect inductor, it is 90 degree. For perfect capacitor, it is minus 90 degree. For RL load, it is between 0 to 90. And for RC load, it will be minus 90 to 0. We have already understood these things, right, in AC analysis. That's why I told at that time, AC analysis, if you can understand, many of the subjects are very, very simple to understand. Even the power systems, measurement, some of the power electronic concepts and machine subjects, these are all related to the AC concepts only, much of the things, okay? So you have to understand the AC analysis properly, then only it is possible to understand remaining all subjects related to that, okay? So we will see this one, okay? So VR, VY and VB voltage we have given. Let's draw the currents, okay? IR, IY and IB, okay? So anyway, current IR lags VR voltage by an angle of phi. This is lagging load, right? So anyway, all the loads are balanced. This is balanced load. So other load is also lagging. Other load is also lagging. Okay, so we'll just draw the currents. So current, this is lagging by an angle of phi here. Okay, so this is IR current. Okay, so similarly this current is also lagging. That is IY current. Okay, same magnitude it will be. Okay, similarly this is IB current. Okay, so this is IB current, RYB phase sequence. You can see here also I am following the same phase sequence. So R is going, after that Y is going, after that B is going, same phase sequence we are just giving here. What is this angle? That will be phi. Yes or no? This angle is also phi and this angle is also phi. Okay, so because this is balanced load, for everything you will get the same angle of phi. Understood, right? So anyway, we need the angle difference between VRB comma IR. VRB vector we have to know, this VRB vector we have to know, and IR vector also we have to know. After that, VYB vector we have to get and IY vector we have to get. Okay, so just check in this, any vectors available for us. IR vector available and similarly IY vector is also available. Understood, right? So what you have to draw now? You have to just draw VRB vector and VYB vector. Understood, right? So we can write down VRB. Just tell me how you can write down VRB. So VRB equal to VR minus VB. Yes or no? VRB is nothing but VR minus VB. Otherwise you can write down like this, right? So VR plus minus VB. Okay, so that means if you add these two vectors you will get VRB. If you add these two vectors, then you will get VRB. Understood, right? So what vectors you have to add? VR with minus VB you have to add. Okay, so that means, so VR vector we have, where is minus VB? So if you take VB, this one, you can able to see, right? So VB is this one. So if you draw minus VB, it will be exactly in opposite to this one. Understood, right? So it will be exactly opposite to this one, VB vector. Understood, right? So anyway, this is VB vector. So same magnitude of this one, okay? Same magnitude of this one. So if you add this minus VB and VR vectors, then you will directly get the VRB vector. Okay, so just for the vector addition we have to extend this one, right, like this. Okay, so in parallel to this we have to extend this, and in parallel to this we have to extend this like this. Okay, so if you join these things, okay, so if you join these things, you will directly get the vector VRB. Understood, right? So VRB you got, and you can check the angle, right? So we can check the angle. What is the angle means? So if you take this one VB, minus VB you have taken like this, other side, okay? So just I will draw this again, just see. So minus VB we have taken. So minus VB means, so it will come like this, okay? Okay, this is minus VB. So we have taken minus VB vector. So total from VR to VY, what is the angle? From VR to VY, what is the angle? 120 degree. We have already seen, right? VR to VY is 120, VY to VB is 120, VB to VR is also 120 because they are in balanced, okay? So they are balanced. So we got 120 degree. Now this VB you are drawing exactly opposite to this. This VB you are drawing exactly opposite to this means it will directly bisect this angle or not. This complete angle is 120 degree. So it will directly bisect this one, right? So that means it is 60 and this is 60. Yes or no? This complete one is 60 degree. Understood, right? So this VB minus VB vector will bisect this angle, okay? 120 degree angle, total 120 degree angle by 60 and 60 like this, okay? It will directly bisect that angle. Understood, right? So anyway, and this VB is magnitude, same magnitude of VR. Yes or no? All the three are balanced, right? VR, VY, VB, all the three are balanced. That means VR vector, VB vector has same magnitude. Once these two have same magnitude, then automatically, if you just see this one, this complete vector, okay, VRB vector, will it bisect this 60 degree angle or not? So directly it will bisect. So you will get this angle as 30 degree and other side this angle as 30 degree. Understood, right? Now you see what you need. VRB comma IR. We need angle difference between VRB vector and IR vector. Okay, where is VRB? This is VRB. Where is IR vector? This is IR vector. Understood, right? So from here to here it is 30 degree. So and from here to here it is a phi, angle phi. Okay, so you can able to see here this is angle phi we have given already. Okay, so this is angle phi and from here to here it is 30 degree. If you ask what is the angle we need, so that is VRB vector. Okay, so VRB vector and IR vector we need this angle. Okay, I am just drawing with this color. Okay, you can see. So that angle we need, that is nothing but total angle is 30 and this angle is 30, this angle is phi. Okay, so total is 30 and this angle is phi. If you calculate, so VRB and IR vectors, and what is the angle difference? But that is 30 minus phi. Understood, right? So this angle we got. Okay, so angle difference between VRB comma IR. Okay, so that will be equal to 30 minus phi. Okay, so you got like this 30 minus phi. Understood, right? So we got the angle 30 minus phi for this one. Okay, so anyway we have to calculate one more angle, that is VYB and IY. Okay, how you can write down VYB? VYB you can write down as VY minus VB, otherwise VY plus minus VB you can write down like this. Okay, that is nothing but VYB. Okay, understood, right? VYB you can write down like VY plus minus VB. You have to write down like that. So anyway, minus VB you have, VY we have, you have to just extend this one like this. Okay, so extend, and this also you just extend like this. So if you just take this one, so already this is 60 we have understood, right? So this is 60, this one is 60 here, from here to here it is 60 and here to here also it is a 60 degree, and if you calculate the equivalent of these two, then it will directly get 30 degree here and here also 30 degree. Understood, right? This is VYB. Okay, so VYB it will be, and we need angle difference between VYB vector and IY. Okay, so VYB vector is here and IY vector is here. Okay, I will just draw the angle. What angle we need? We need the angle difference between VYB and IY. Understood, right? We need this angle. What is that angle? That will be equal to the 30 plus angle difference between VY and IY is the phi angle. Okay, so we have given already. So that is phi angle. So 30 plus phi you will get. Understood, right? So the angle difference between VYB comma IY. Okay, so that will be equal to 30 plus phi. Okay, so these angles we have to get. Okay, so these two angles we got now. Understood, right? So one angle is angle difference between the VRB comma IR. VRB is here and IR is here, so angle difference is 30 minus 5, and if you take other one, that is 30 plus 5. Understood, right? So 30 plus 5 you got like that. Okay, so if you calculate all these two angles, now you need to substitute these angles here. Okay, in these wattmeter readings W1 and W2, we have to just give the angles. Okay, substitute those angles there. Understood, right? So anyway, we will write those things now. Okay, so we will write these things. So just try to see the angles. Okay, so we have to write down these angles, and I'm just writing W1 equal to VRB IR cos of angle difference between VRB comma IR. This is first wattmeter reading, and second wattmeter reading W2 equal to VYB IY cos of angle difference between VYB comma IY. Okay, so this is a second wattmeter reading. Okay, we have to substitute those things. Okay, so we'll substitute. One is 30 minus 5, another one is 30 plus 5. You got already. Okay, so just remember that. Now tell me, this is star connection, right? For star connection and star balanced connection it is. Okay, so star balanced connection. For star balanced connection, we can give some conditions, right? Star balanced one. Okay, so balanced connection, star balanced connection. So we can directly give one thing. So VRB equal to VYB equal to VRY equal to VL. That is line voltage. Yes or no? Between two lines it will be. We can give that one as line voltage. Okay, so we can give that as line voltage. And similarly IR, IY and IB, these are all line currents. So anyway, we can take these things as the phase currents also, no problem, but it is line current also, so I will just consider as IL. Okay, so all this is balanced one. All the currents and all the voltage will be same for this one. Okay, so all line voltages are we can take as VL, all line currents we have taken as IL here. Understood, right? We'll substitute these things in wattmeter readings. So we'll get W1 equal to, so what is the W1 reading? VL into IL. Okay, you can substitute here. Okay, so substitute in this one VL into IL into cos. Tell me what is the angle you got? VRB comma IR. What is the angle you got? That is cos of 30 minus 5 it will be. Understood, right? 30 minus 5 you got. Under W2, so W2 you got VL IL cos of angle difference between these two is 30 plus 5 you got. Okay, so these are the two equations you have to remember. Okay, for your exam you just have to remember these two equations. Okay, so one wattmeter reading is VLIL cos 30 minus 5, another one is VLIL cos 30 plus 5. Okay, so these readings we just have to remember definitely. Okay, so if you can remember these things, many of the problems whatever they are giving from the wattmeters you can able to answer easily. Okay, I will tell you whether we have not checked yet. Okay, whether this 2 wattmeter method is working or not, whether it is reading 3-phase power or not, we have not understood. Okay, that means what is 3-phase power? P 3-phase equal to root 3 VL IL cos 5. You have to get like this, then only this wattmeter 2 wattmeter method is working. And similarly reactive power 3-phase, so that is root 3 VL IL sin 5. Okay, so this is the reactive power. You have to get this active and reactive power. Okay, then only this 2 wattmeter method is working. Understood, right? Anyway, 2 wattmeter methods, 2 wattmeter readings we got like this. We will just add these two. What we will get, we will check. Okay, so if you add these two, so just add W1 plus W2. If you add, so VLIL will be common into cos 30 minus 5 plus cos 30 plus 5. Okay, so anyway, this is cos A plus cos B. You will get 2 cos A plus B by 2 and cos A minus B by 2. Okay, so we will get like that. So directly we can add these things like, so VL IL into 2 cos A plus B by 2. This is A and this is B. Okay, so A plus B by 2, so that means 30 minus 5 and 30 plus 5 divided by 2 means cos 30 you will get. Okay, So cos 30 and cos A minus B by 2. Cos A minus B means minus 2 pi divided by 2 you will get. Anyway, cos minus phi is nothing but cos phi only. So we'll get as cos phi. Okay. So like this you got. Okay. So anyway, if you substitute this one, VL IL into 2 into what is cos 30? Cos 30 is root 3 by 2. Okay. So root 3 divided by 2 into cos phi you got. Okay. So this is the complete one. So 2 will be cancelled. You will get as root 3 VL IL cos phi. Okay. So this is W1 plus W2. Understood, right? This is W1 plus W2. This is W1 plus W2, and this is nothing but 3-phase power. 3-phase power in the network. Understood, right? 3-phase power in that load is nothing but the complete W1 plus W2. That means if you add those two wattmeter readings, you will directly get the 3-phase power. Understood, right? So 3-phase active power you can get directly by using 2 wattmeters only. By using these 2 wattmeters, you can get the complete active power in that network. Understood, right? So W1 plus W2 is root 3 into VL IL cos phi we got. That means we can write down P3 phase in the network equal to W1 plus W2 directly. Understood, right? So this one also we have to remember. Understood, right? So that is active power only. Okay. So total active power in 3-phase network you can write. Okay. So total active power in 3-phase network. Okay. 3-phase load. Okay, so we have just checked for the balanced load only. You can check for the unbalanced load also. You will get the answer. Okay, so this 2 wattmeter method will work for both. Okay, both balanced and unbalanced loads, and star connected load and delta connected load also. Okay, so anyway, this is active power only we have calculated. If you check the reactive power, what is the reactive power? So if you just check W1 minus W2, so you will get like VL and IL. You can see your copy. So I have just removed here. You can check your copy there. So VL IL will be common here, and cos of 30 minus phi minus cos of 30 plus phi. Okay, so anyway, this is cos A minus cos B. Okay, cos A minus cos B formula. So we will get minus 2 sin A plus B by 2 sin A minus B by 2. Okay, so you can learn these things in trigonometry. If you get any doubt in trigonometry, just check again. Okay, so we have to understand some trigonometry formulas here. Okay, so that is VL IL into minus 2 sin A plus B by 2. A plus B by 2 means you will get 30, 60 by 2, that is 30. Okay, so into sin A minus B by 2. A minus B by 2 means you will get minus 2 pi divided by 2, you will get minus phi. Okay, so anyway, sin of minus phi is nothing but minus sin phi. That minus and this minus will be cancelled, and you will get sin 30, that is 1 by 2. Okay, sin 30 is 1 by 2, so 2 and 2 will be cancelled. You will get VL IL sin phi. Okay, so this is W1 minus W2. Understood, right? So but see the reactive power, that is root 3 into VL IL sin phi. That is total reactive power. What is this reactive power? Is this for single phase? This is not for single phase also. Understood, right? This is not for single phase. Single phase reactive power you can give as V phase, I phase. Okay, sin phi. This is single phase reactive power, but it is in line voltage and line currents. So there is not single phase power. Understood, right? That is not single phase reactive power. This is some reactive power component only. Understood, right? This is some reactive power, not single phase, not 3-phase directly. But to make this one, I will just multiply this one with root 3 here. Okay, so root 3 into I will take. Okay, so if you just multiply with root 3, this is root 3 VLIL sin phi. Now you can tell this one as reactive power. Understood, right? So we got, so what is the complete reactive power? Q3 phase we can give as root 3 into W1 minus W2. So this is a complete reactive power in the load. Okay, so by using these two wattmeters only we are getting. So see what we are doing. So for some load they have given for you, okay, some three-phase load they have given for you. You have connected two wattmeters, however we have connected, okay, so like that only you have connected two wattmeters, and two wattmeter readings you can see as they have indicated, right? So W1 reading it has indicated, and W2 reading also it has indicated. So if you add those W1 plus W2, you can get that load three-phase active power. Understood, right? And if you get W1 minus W2 and multiply with root 3, then you can get complete reactive power in that three-phase load. Understood, right? This is three-phase. This is three-phase reactive power. This is three-phase active power. Understood, right? This is total reactive power in three-phase load. Okay, so total reactive power. Okay, so this is total reactive power in three-phase load. Understood, right? So this is complete reactive power in that three-phase load. Okay, so that's how we have to understand the active and reactive power. That means using these two wattmeters only we are measuring the active power and reactive power. Understood, right? So that means by using this two wattmeter method you can measure any of the three-phase power. Okay, that means active or reactive power. Understood, right? Similarly, we can find out one more thing. I will just write the formula. Okay, just see here. So we can just write the formula here. Okay, just a second. So the formulae are just three-phase active power we can give as so VL IL. Okay, so root 3 VL IL cos phi, that can be given as W1 plus W2 we have given already. Okay, and three-phase reactive power we have given as root 3 VL IL sin phi, and we can give that as root 3 into W1 minus W2. Okay, so we have just understood these two, and once you have active and reactive power, can you give the power factor angle phi? Tell me, can you give the power factor angle phi for that load? So power factor angle phi equal to tan inverse. We might have learned this one in networks, right, in AC analysis. What is the power factor angle phi equal to tan inverse reactive power divided by active power? So Q3 phase divided by P3 phase. We have to give like this. Using the wattmeter powers we will give. That means root 3 W1 minus W2. Okay, so we can give as tan inverse root 3 W1 minus W2 divided by W1 plus W2. We can give like this. Okay, so this is the formula we have to remember. Okay, so these are all the formulae that will directly get the questions. Okay, so these formulas only they will give the questions. They will give W1 and W2 readings. Directly they will ask what is the power factor angle, otherwise what is the power factor. Okay, so once you calculate the angle, we have to get the power factor also. Okay, so power factor is nothing but cos of this angle is nothing but power factor. Okay, so this is which method? 2 wattmeter method only. Okay, so everything is 2 wattmeter only. So by using 2 wattmeter you can measure active power and reactive power. Okay, so some questions will be there on this. So by using 2 wattmeter method, can we measure reactive power? We can measure the reactive power also. So you just have to do W1 minus W2 into root 3. Okay, so we have already seen, to get the complete reactive power in that three-phase network, we just have to do W1 minus W2 into root 3. We have to calculate like that. Understood, right? So that's how we have to understand the complete active and reactive power in the networks and in the three-phase load, and the power factor angle phi equal to tan inverse root 3 W1 minus W2 divided by W1 plus W2. The same formula only they might have given like this. The tan inverse root 3 W2 I will take as common. So we will get like, so root 3 into W1 by W2 minus 1 divided by W1 divided by W2 plus 1. Okay, so we can write down like this, and W2 will be cancelled, whatever you have common. Okay, so you can write down like this, the same formula. Okay, in some exams they will give like this, so no need to confuse, every formula is same only, right? Just W2 we have to take common here. Okay, so like this we have to understand the power factor angle also. Understood, right? So anyway, for your understanding, I will just draw the vector diagram again. Okay, just see the voltages we have taken. Okay, so voltages we have taken VR, Vy and VB. Okay, so VR, VY and VB we have taken. We need angle difference between VRB and IR. Okay, we have seen already for the first wattmeter. So we have just taken minus of this. Okay, so minus VB we have taken. So this is minus VB, and if you add these two, extend these two, so that means for the adding you have to draw the parallelogram. So we have just drawn the parallelogram, and similarly here also for this. Okay, VY minus VB we have to calculate. That means just add these two and extend, okay, as the parallelogram. So you will get the equivalent as, so this is VRB, okay, and this one is VYB. Okay, so we got two voltages, and if you check what is the angle difference between VR and VY, that will be equal to 120. So if you check this angle, that is 60 degree, and from here to here also it is 60 degree. Okay, and if you check this angle, that is 30 degree. Okay, we have already seen, that means this is also 30 degree. And where is IR? IR is here. Okay, so we'll just draw this one. So IR angle is here, IR vector. Okay, so IR is here. What is this angle? That is phi. Okay, so this angle is phi, and similarly where is IY? So this is IY. Okay, so that angle is also phi angle. Okay, we need this angle. So what is this angle? VYB and IY, that is 30 plus phi. Okay, so what is this angle? Angle difference between these two, that is nothing but 30 minus phi. Okay, so just for understanding I have given again. Okay, because at that time, so all the angles we used to explain, right? Okay, we will not get properly, so that's why I have just given it again. Okay, let's try it. Anyway, some more points we have to understand from this one. So you can check, right? This is the star connection. In star connection, line voltage have more magnitude or phase voltage have more magnitude. See, this is the line voltage and this is the phase voltage. Understood, right? Now see, phase voltage has more magnitude when compared to line voltage. Understood, right? So that means one more thing we have to understand. VR is this one and VRB is this one. What is the angle difference between the line voltage and phase voltage? So what is the angle difference between line voltage and phase voltage? That means we can get here 60 degree, 30 degree of angle difference. Understood, right? So 30 degree of angle difference is there between those two. Understood, right? So like that we have to understand. Between these two also 30 degree is there. If you draw one more, between those two also there will be 30 degree of difference. Understood, right? So like that we have to see the angles. Okay, so and magnitudes of these vectors. Okay, voltage vectors and current vectors. Okay, anyway, in delta connection also we can make all these things. So actually if you have any time to understand the vectors separately, you just understand the three-phase networks, spend one day or something for the three-phase networks, you will get many of the concepts. So solve some 20 to 30 problems on three-phase networks, so you will definitely understand many concepts that will help you to understand many of the power system concepts and power electronic concepts and machine subject concepts. Okay, so before understanding these subjects, just learn the three-phase networks and learn the powers and angles and vector diagrams, everything. Okay, so before understanding these three subjects, okay, that will be more helpful for you to understand. Okay, so that's how you have to give the powers in three-phase network by using the 2 wattmeter method only. Understood, right? So this is how you have to understand the 2 wattmeter method. Okay, so we have just understood the 3 wattmeter method works for both delta connected load and star connected load, and it will perfectly work. It is unbalanced or balanced. Okay, so for everything this 2 wattmeter method works. Okay, so actually there is 3 wattmeter method also. Yes or no? There is 3 wattmeter method also. That is nothing but connecting each wattmeter in all the 3 phases. Then there is nothing to learn, right? Directly powers we have to give. So it will read the power anyway. Understood, right? So there is nothing to learn. So that's why 2 wattmeter method we have learned, and those formulas whatever I have given, the the first wattmeter reading W1 equal to VLIL cos 30 minus 5. Okay, first one is minus 5 and second one is VLIL cos 30 plus 5, and if you add these two you will get the active power. If you minus these two and multiply with root 3 you will get the reactive power, and phi equal to angle phi, power factor angle phi equal to tan inverse root 3 W1 minus W2 divided by W1 plus W2. These formulas we have to remember anyway. Okay, so in every exam you will get these things. In our next session we will see the some of the cases about this 2 wattmeter method. After that we will solve some problems on wattmeters. Okay, thank you so much.